Okay, everybody, today we're going to take notes on exponential modeling, and we're going to look at exponential growth models. We're also going to use some of the things we did yesterday with graphing exponential functions to help us as we solve real-world problems that are based on exponential functions. So the handout that you're going to need for today is this one. That's the first one we're going to work on. Make sure that you have the one that says Increasing Exponential Models to get started with. And this is going to be, let's see, page 129 in your notebook. And today's date is 5/13. Okay, so we're going to use this first exercise to help us understand the exponential growth equation that you see in the box below. So we're going to talk about investing money into a savings account, and it looks like here that we have a 5% interest per year. So this is part of our growth rate. And we're going to start with $400 in our account initially. So that's important information that's going to help us solve this problem. So the first question is, how much will the savings account increase by over the course of the year? So I need to figure out what 5% of my initial amount is. So 400 times 0.05. Whenever you're working with percents, you have to convert them to decimals. And that actually ends up being 20. So we're going to increase our amount in our savings account by $20. So that would mean at the end of the year, we would have 400, was how much we started with, plus an additional $20 in our account. So that's $420. All right, probably the most important problem in this section here is this one. Because rather than just multiplying by 5%, I can actually multiply by a single number and jump from 400 to 420. And that's going to be my growth factor. So let's think about what that would be. If I want to go from 400 to 420, I would need to multiply by 1.05. The one part is for the initial amount, and the 5% is the growth rate.
Mrs. Smith, Mila Smith, please come to B18, the conference room, please. Thank you.
It never ends. All right, so now that we know that we can multiply our initial amount by 1.05 to get to our 420, we can figure out how much money we have in our account after any number of years we want, because each year we're going to multiply the previous year's amount by the overall growth factor, which isn't just going to be 5%, it's going to be actually 105%. So if I want to find out how much money we'll have in the account after 2 years, so to find the amount of money in our account after 2 years, we're going to have to take the amount after 1 year, and we're going to need to multiply it by 1.05, or 1 500ths again. I'm going to use the calculator to get that number for me. All right, so 400 times 1.05. This will be how much money we have after 1 year. You can see that that calculation really does give us 420. And then I'm going to just hit the multiply button, and I'm going to multiply by 1.05 again. And this is how much money we'd have in the account after 2 years. So that's $441. And we can figure out how much money we have in our account after 10 years if we just keep hitting the enter button. So you got to count along with me. So this was after 1 year. This is after 2 years. So this would be after 3, 4, 5, 6, 7, 8, 9, 10 years. So I will have after 10 years, again, I've multiplied by 1.05 10 times, according to my calculator, $651.56 if I round that to the nearest cent. It's interesting in the table here, you can really see how this is growing recursively by repeatedly multiplying. I'm taking my previous answer and multiplying by 1.05. That gives me 590 times 1.05, new answer, 620, and on and on. Okay, so now we're ready to write a function. If after 10 years I have multiplied by 1 500ths 10 times, then after t years, I will have taken my $400 and multiplied it by 1 500ths t times. So there's the formula or the equation that will allow us to figure out the amount of money after any number of years. This next problem we want to do is figure out how long it will take to double. When we double our investment, if we start with 400, that means we want to know when there's 800 in our account. So I'm going to use a table on the calculator to determine that. So what we need to do is get the equation entered into y1 first. So that's going to be 400 times 1.05 to the x. And now we're going to go to the table. We're going to set our table up to start at 0 and increase by 1 year. And then second graph is where table is. And so you can see those were the same numbers in this Y1 column that we had on the home screen a few minutes ago. And if I scroll on down to where we exceed 800, it's between the 14th and 15th year. So I'm going to write this down on my paper. So S of 14 is 791.97. S of 15 is 831. And so we will double our money between the 14th and 15th year. All right, let's take a look at this general formula now, because we can use what we did in this problem to create a general growth equation. Okay, so Q of t is our amount after t years. Q of 0 is the amount present at time t equals 0, and a lot of times we'll call this the initial amount, so let's add that here. And then P is our percentage of growth. So in the problem up above, we were growing by 5%. And so 1 plus 500ths is where we got that 1.05 from. Remember, this is going to have to get turned into a decimal. That's why that information is right there. So let's see if we can use this formula to quickly write a savings account function, or a savings account equation. So S, or actually we could just put S of t. We're starting with 250. That's like the Q sub 0. And we're going to have 1 plus 3% in decimal form. So in decimal form, 3% is 0.03, or 300ths. And that's going to be raised to the t. A lot of times people forget their variable. I almost did. So make sure that you remember to put that there. If we compare this equation to the equations over here, you can see that choice number 2 is the correct response. All right, let's go do a little bit more of a challenging problem. We're also going to look at the graph of these exponential models. So if we have unrestricted population growth, we can use that to model with an exponential function, a growth curve. All right, so we have to, when we're reading a word problem, identify our growth rate and our initial amount. And we're going to start counting time in this problem from the end of 2005. So the P of t equation is going to be, I'm using P because this variable was P, 6,500 times 1 plus 0.025, that's 2.5% in decimal form, to the t. Or if I want to just add those two numbers together here, and this gives me my overall growth factor of 102.5%. The next thing we want to do is come over here and make a sketch. So the initial amount is your y-intercept, because if I make time 0, then anything to the 0 power is 1, And so we'll just have 6,500. So we'll go over here and we'll just mark 6,500 on our graph. And then this is an exponential curve, so it's going to be increasing, at some sort of a curved rate. And we wanted to put on this problem how much we would have after 50 years. Notice that after 50 years, it will be the year 2055 because we're counting time since 2005. All right, let's go over here and type this in. So 6,500 times 1.025 raised to the x. If you don't have that in there already in your calculator, you have to hit the caret key right here. That's the exponent button. All right, let's go to the graph here. Actually, let's go back to the home screen first. I want to just figure out 6,500 times 1.025 raised to the 50. I want to see how much the population would be. Okay, that's 22,341. Rounded to the nearest whole number. So the coordinates of that point would be 50, 22,341. This is going to help me create the scale on my graph. So go to Window, 0 to 50, running up for 50 years. And you can see I selected to go up to 25,000 so that I easily fit 50 years for the x values on my graph. So here comes that exponential growth curve. You can see it's not even as curved as I made mine. All right, let's keep going here. We want to use our model to predict the number of residents at the end of 2010. Well, we don't really need the graph to do that. We just need to plug in 5 because this is 5 years after 2005. And so 6,500 times 1.025 to the 5th. We could go to the table and look that up, or we could go back to the home screen and calculate this. So 6,500 times 1.025 to the 5th, 5 years since 2005, is 7,354. I'll write it down here so you can get it in your notes. And again, that's rounded to the nearest whole number because we're talking about people. All right, graphically, we want to figure out when the population P is at 10,000. So now what we have to do is figure out where the 10,000 mark is on our graph, and then figure out what time interval that corresponds to. So we're going to use the intersect button because the intersection point gives me the solution to the equation. So basically what we're solving is this equation, 10,000 for my P of t equals 6,500 times 1.025 to the t. All right, so we've got to go back to the calculator and find the intersection point. But first I need to add 1,000 into 10,000 into the equation. Okay, so here we go. Graphing these, we're going to add that horizontal line in, and then I'm looking for the intersection point right there. So on the calculator, it's second calc. Let me zoom in just a little bit. Okay, second calc. Then we're going to go to intersect. Press enter. And then when you arrow over to the intersection point, we need to press enter 3 times. 1, 2, 3. So I can see the population will be 10,000 sometime between the 17th and 18th year. So that was 17.544. Okay, so determine the year that the population reaches the 10,000 mark. So I would need to take 17 and 18 and add that to 2005. So 17, so between 17 and 18 years after 2005.